Okay, I do not see any question. Also, I would like to ask, is there any topic that you want to recover in one of your tutorial? Then I can ask to recall. Is some basics you need to recall from real analysis or something we have discussed? All right, I do not see any question, neither any comments. So let's begin. So yeah, we are going to probably give the shortest possible introduction of quantum mechanics. So let me begin with the axioms. So people who are from maths background, they know there are axioms in mathematics, and these are like a fixed object. And the idea is that you derive everything from axioms. This approach is not um, exactly same in physics because the axioms of physics changes with time. Okay. In particular, we want to put the axioms in such a way so that we can um, explain as much as possible our environment or universe and put the axioms as less as possible. So from minimal number of axioms, we want to explain maximum number of things. And as we are progressing, our understanding is changing, and so is our axioms. So what I am going to write or explain today is more or less the standard thing, but as I told, it may change. So the first axiom, UM1, so first axiom is that when we have, um, I go to this picture again. Okay, better draw it again. So as yesterday we discussed, there is the nature. And if we take a, so it's our whole observable universe, okay? So if we consider the whole part or maybe a small part, the first axiom is that associated to any part of experiment or our universe, we associate a Hilbert space. So okay, maybe I follow yesterday's color convention. So the blue thing is our nature. And we consider, so this can be the whole also, say part of it. And then we have our mathematical world. And that's our Hilbert space. Okay. So first axiom, to every quantum system we associate a separable Hilbert space. And also complex. Maybe I write it here, complex Hilbert space. Why separable? We will discuss maybe end of today's lecture. And you will see that most interesting examples, in particular, if you take thermodynamics seriously, then that's more than less what we need. Okay. Now, what do we mean by quantum mechanical system or the system Hilbert space? So this may mean many things, actually. For instance, atom, elementary particles, phonons, spin, and many more things. Okay, so those who are from maths background, they are might not familiar with this. In this case, a system. I mean, we will describe something. So these are like some of physical entities. So for this, we will associate a Hilbert space. And if we have a different type of quantum system, then we cannot do superposition, right? So say Hilbert space of atoms and Hilbert space with the spins not always match up together. Okay, next one. Is a state okay, let me first write a state and then we define, because now I just realize I haven't defined what is a state actually. But let me write it. So mentally, so you can think like, okay, at some particular time, you consider some ensemble of identical quantum mechanical system, okay? So the procedure of preparation of ensemble ensembles of identical quantum mechanical systems corresponds to the state uh, so the rho of the system. Now, before you ask, what is the state? So, definition. So, this definition is very generic. You don't need to be separable or even finite, infinite dimensional. So, H is a Hilbert space. So, it may or may not be separable. It can be even finite dimensional. By a state, a rho, we mean a positive trace class operator of um, okay, trace class operator. Okay, let me first write of trace 1. That means rho is positive. You know what is the meaning of positivity? It's a trace class. We have discussed trace class operators, and its trace is 1. Okay, so we will discuss a bit more about traces, but later. Let me just write first these axioms, and then we come into details. So again, in this picture, when you have, say, you have one this blue part. So we associate first a Hilbert space, and then we associate some state, and you know state is a linear functional on bounded operators here. So some state is there. So say if this is your universe of experiment, then state is defined all over here. Okay, maybe I write here. So positive space plus, yeah, all over Hilbert space. Keep in mind, that's really important. Okay, next. So what happens after measurement? Yeah, so we have this thing. So we prepare something, and now we have some experimental device, and we do a measurement. If the quantum system is in a state rho. Okay, let's use a notation state. So this is set of all states, okay? At time t, and E is some operator on H is true. True means experimental outcome. After a measurement, at time t, then the system's state immediately afterwards means just after the experiment is rho p. This is given by p rho p divided by trace of rho p. If there is something called pure state, then there is a simplification of this expression. We will come it a bit late because I haven't defined what is a pure state yet. So in physics literature, this is something known as collapse of wave function or collapse of state. So wave function, again, this terminology we haven't introduced yet. I shall introduce maybe after half an hour. So why it is called collapse? The reason is, say you do an experiment here, okay, at some time. Oh, sorry, at some time. So you have a state rho, and then you wait a while, and then you experiment again there. So after experiment, you get another state that is the rho p, and rho p is given by this expression. So this is called collapse in this sense. You can think that before experiment, from rho, so at time t, to rho p, many things can happen, and we will see maybe later today or next lecture that in particular there is a saying that basically anything logically possible or allowed by quantum principle is possible. But once we do the measurement, then only this will be outcome. So this measurement, in a way, collapse all other possibilities, and that's why it's called in way. Maybe I write state collapse. We will come to more popular word, wave function collapse, but later. Okay. So I told you like we are doing some experiment, right? And what we are describing is actually uh, different. What happens before, after experiment, sort of thing. Now, what do you do in experiment? We measure something. We have some experimental device, and then we measure something. For instance, this lecture can be think as an experiment. Um, in which sense you joined in the Zoom, and once you joined, then you have other participant and me, and you can switch off, and this or you can leave, and once you leave, then you are in this situation. So this is like your action, and before we were in this situation. Okay. But in this case, there is no collapse because even if you leave, things are happening, right? We are continuing. But since in this case, we are really isolating, for instance, if I as a admin leave or off it, then everything, this discontinuity happening, we have a lecture recording and suddenly it will be just off. But this is not considered at collapse. Why? Because nothing is saying that if I do that, then this is not supposed to happen. In a way, collapse is the notion uh, used to see that, okay, you have kind of evolution. We will see what is the quantum evolution. But once you do experiment, it doesn't follow the quantum evolution. Immediately after experiment, no, so I mean, it doesn't follow, doesn't mean that literal sense that it gives something very different. So the quantum evolution tells you that five possibilities can occur, but experiment picks just one. In that sense, it's collapse. Okay. Now, as we are talking about experiment, and without experiment, what can we actually say about physics? Because at least my understanding, physics is an experiment subject. There might be people who are not happy with this statement, but yeah, I don't see if you cannot falsify anything with experiment, uh, how you differentiate physics from a non-falsifiable subject. But let's not go this philosophy right now. Now, when we are talking about experiment, question is that what what sort of experiment is allowed? Can we do everything in experiment? We are coming. We are coming expectation value a bit late. We didn't study this collapse formula before in quantum mechanics. Okay. Uh, I think you might have seen this wave function form, but thanks for your comment. Let me go the wave function form, and then if it is familiar, then good. If not, then we will explain more. But thanks for your comment. So, what we are doing, like, what sort of experiment is allowed? Is all sort of experiment is allowed? And it depends on actually your system. So quantum mechanics allows certain experiment, quantum field theory allows even restrictive set of experiment. Now, what sort of experiment allowed? If we keep aside this question is that when we do experiment on what, right? For instance, if you want to do an experiment, say you want to measure your weight. So what you do, you go to some weight machine and you stand there and then see the needle. Okay, that means your weight is something that is experimentable, right? Um, but is everything experimentable? For instance, you say your hair color. Yes, it is. I mean, you just check the color of your hair. You say, how about my blood pressure? Yes, that's also experimentable. But if you call how much I dislike the lecture course, is it experimentable? Or how far I like, if any of you really like it? You can say up to some extent, yes. if I dislike it, then some of my blood pressure and other parameter changes. But to best of my knowledge, it's not really one-to-one yet. Like you can quantify based on something. You can quantify up to some extent, but not everything perfectly. Or like human feeling, for instance, love, hatred. There are some thing, but not everything. So that means we have to differentiate what we can measure in experiment and what we cannot. And again, this has two different flavor. One is that is it experimental limitation or in principle? So first we talk about in principle. We say that, okay, we do not know yet whether everything is possible or not, but whatever is possible to observe by an experiment, it may be everything, it may not be everything, that we will see later. We give a specific name, and the name is observable. So what can be observed? So next postulate. Observables. So these are something that can be observed, yeah, by the name. And what are these? I mean, what are these? I mean that this is an observable, but how to describe them in our mathematical world? Hmm, maybe I right. Every observables in quantum mechanics is described by a spectral measure So remember, spectral measure depends on which operator we are considering. So if, okay, maybe, okay, let me continue. So spectral measure PA on R. So spectral measure is on the Hilbert space. So you know what is spectral measure. Put it here. Um, yes. So every observable A, and this corresponds to, okay, let me write, I can write it like this. So every observable in quantum mechanics are self-adjoint operators on a Hilbert space. Is described by a spectral measure on R. If, okay, so again, remember this picture. So what we are trying to do is actually we are trying to get a map from here to here. It's not visible probably. Yeah, so this is our physical world and this is our mathematical world. Um, math, or maybe theory is better word. This is our nature. Okay, so what can be observed here is denoted in mathematical world by self-adjoint operators on Hilbert space, and this observable is actually described by a spectral measure associated of this operator on H, on R, and operator is on Hilbert space. Okay. Now it may happen that we are not observing everywhere. Okay, so maybe we want to observe only here. Okay, so that means we need a subset of our physical universe. And how do we describe it? So if E is a Borel set, R, then E gives what is called, let me write here, is the reading of a measurement of A. So there are two A. Hopefully you understand. One is the operator A. Maybe I write it for clarity. A falls in the Borel set E. Okay. So that's how this expression is to be understood. And with this, I also want to add one point. So we say the observable B is a function of A, and then how do you write f of A? Now, hopefully you remember how to define function of a self-adjoint operator. See? So we say an observable is a function of A, and we write it this way. When there is a measurable, this measurable means in the measure theoretic sense, which I haven't unfortunately described at all. Map F from R to R such that the spectral measure of the observable now B on the Borel set E is, so we know this is a function, then how do you, it's a spectral theorem, so that we know, and then you just take pre-image. Remember, this is pre-image, not the inverse. Okay. All right. So now we know what is observable. So, okay. So far, what we have learned, maybe let's go to our picture. We have got two types of mathematical object. One is a state, and another is observables. Of course, we also have a Hilbert space. So the map from physical world to mathematical world tells that we need right now at least three mathematical object. One is the Hilbert space, and that's our first lecture. Yes, what is the Hilbert space? Now you see. So we have this question where this is important to understand physics. So unless you know what is a Hilbert space, what's the difference between a complete inner product space and just an inner product space, how can you formulate this? You can just say that then it's just a word. And then the experiment corresponds to two things. One is state, another thing is observable. So where you do experiment, and to describe observable, you need self-adjoint operator, and that's why we try to emphasize so much about self-adjoint operators. And to describe states, we need trace class positive functionals, which we described actually yesterday. Okay. So some of you had this question, which I really, really appreciate. So is it clear why we need these functional analytical notions to describe even the very basics of quantum mechanics? Is it clear to all of you? Because that's really fundamental. If it's not clear, then I mean, you can compute many things, but your understanding will always be shaky. So are there questions about the very, very basics of how we model nature in terms of quantum mechanics and why these terminologies are really important? So I do not see any question, but yeah, please feel free. So now, let me give few words. Why these are taken at axioms? Yeah, you can axiomize anything, but why this is taken? First one as a Hilbert space, it just turns out to be okay. There is a reason why we need a Hilbert space, but at this point, I haven't talked about this. Some of you already talked about this probability measure, conservation, and thing that will show up later. And so we'll see how Hilbert space is necessary. About state, so what we do an experiment. An experimental outcome is always a number, right? It can be, and okay, you can put positive, negative, but it's a number. And if you don't do anything, then it should just give as it is. So very loosely, that's your mental picture. You do not do anything, then it's just no. Sorry, this is not. This is about normalization. So that if you take the whole system and you integrate over everything, then you should get just one. So one means you consider over all these things, and one means this. And if it is not, then zero. Okay, so that's your normalization. Now, in general, not every bounded operator trace is one. Yesterday we discussed it. So we need to specify this type of operator which has positivity and trace class, and that's why actually we introduced trace class operator yesterday. Okay, so that's how the mental picture, why the axioms are like that. This is why non-positivity comes, because when you do an experiment, we get a number, and usually number is positive something. Okay, and this is the normalization factor. We will discuss about it a bit later. And now the observables. Why self-adjoint operators? And the reason is self-adjoint operators has real spectrum. Only self-adjoint operators has real spectrum. So you do not have any other choice except self-adjoint operator to associate something with observables. And hopefully now it's even more clear why we need this fractal theory. Because unless we know self-adjoint operator has real spectrum, how can we say which operator corresponds to our observables? And that was the clue why it was used. Okay. Any questions about why, how, or how to understand this thing? No? Okay, clear. Thank you. Okay, now let me go first with these axioms and then I come back to the, since stress is one, does it mean density matrix? Yes. So you can consider state and density matrix same thing. It's just different name. Yes, so I can write where is the state. Uh, Thanks. Yeah, I think density matrix is usually more used word in physics literature. Okay, any other question? Okay, I do not see. So far what we have described is that like in static situation, right? We want to do some experiment and what happened if we do an experiment and on which we can do experiment, like what is experimentable, um, this sort of thing. But we haven't described anything about how to put this is okay, let's put this way. When we have that we probably using is entanglement entropy. You mean, so could you explain what you mean that we probably using in entanglement entropy? You mean using density matrix in entanglement entropy or what?
Yes, sir. That's what I'm meaning. We use the density metric in entanglement entropy. I think uh, that I read before in the when I am reading about the causal graph, causal set theory. I think I see there's a density metric a lot. So.
Yes, I mean, of course. So entanglement is a property of a state,
Mhm.
and to describe entanglement of a state, definitely you need density matrix. So yeah, I mean, that's natural, right? Because if something is a property of state, then you need a state, and a state is, I mean, just a different word, density matrix. But there are, at least several entanglement entropy. So usually when you talk about entanglement entropy, it's better to specify which entanglement entropy. But maybe you want to mean that to describe entanglement, we need a state, of course, because entanglement is a property of a state.
Okay. Thanks.
Okay. Yeah, and also density matrix you use in statistical mechanics, actually. Yeah, we will see a bit later. Okay, so what we are talking that, so far everything is like a static. You have a particular time and you do something, and then you have some way to describe it. So that's our mathematical universe. Now, in physical universe, if there are two situations in two different time, yeah, so say something is happening at time t equals to 0 and something is happening time t equals to t, then what it corresponds. So maybe there is an issue that you go a sort of time evolution. Maybe it's getting messy, so I just, yeah, maybe I use a different color. So yeah, you probe something here at time t naught or t0, and you want to probe something here at time t. So what will be the situation in this mathematical universe? Okay, so t naught t. And this means that if you have a given observable at t naught, how the observable is evolved at t. You can also ask the same question for state. And that's it's called time evolution, right? Evolution in time. And that actually gives the dynamics of a theory. So there's our dynamics. So there exists a self-adjoint operator on Hilbert space called the Hamiltonian. So those who are familiar with classical mechanics or symplectic geometry, I think you might also heard Hamiltonian there. If yes, there is a difference between that Hamiltonian and this Hamiltonian. If not, then you take this as your starting point. Hamiltonian of the system which corresponds to the total mechanical energy of the system. I write something about frame because I was avoiding this desperately. So usually, I mean, not usually, but I mean, historically, when we describe something, we use some sort of frame or reference frame of coordinate system to describe it. And so far, whatever we done, that is, so by a system, I mean we pick a frame and then we are describing. And that's how it happens. Now I wrote it explicitly because Hamiltonian depends on this. Okay, so those who are familiar with relativity, Hamiltonian is not a relativistic invariant quantity, which is a bad property, but this is what it is. So that's why I just wrote this is a frame dependent. Here it really matter. But anyway, whole quantum mechanics is a non-relativistic theory, so it's not a big issue. That's why without talking about frame, you are not missing much. Okay, total system such that. So those who are not familiar with symplectic geometry or classical mechanics, you just take this as your starting point. The spectrum of H is lower bounded. That means there is a lower bound of this. Okay, something, some constant. Okay, and such that this. Okay, let's put numbers 1, 2. If the system is at time t is, so by system we mean state. You can take also observable. It, then the state plus a tall is given by, so rho p plus tall is given by some unitary operator u tall rho where the system was, and u tall inverse where u tall is the operator defined by e to the power minus. So there is a sign convention actually. In my case, it's minus, but you can also get it plus. We'll see how it comes. So it depends on where you put inverse. Tau h cut capital H where this is called time evolution operator. Okay, so now we have a dynamics of the system, and since this gives us dynamics, that's all called naturally called time evolution operator. So now regarding this time evolution, oh sorry, I missed I. So at this point, I will discuss it a bit detailed now. But at this point, you just take this an operator. So this is the time evolution operator, and again, you can see this is a function of an operator, and now you know right how to define function of a self-adjoint operator. But in this case, you have So even more, I would say even a better description that we will see. Okay, so that's kind of our beginning postulates. We will discuss another postulate probably end of today's lecture or tomorrow. But yeah, let's that's our starting. So I give you a bit time. Yeah, maybe here. So time evolution is okay. So just to give you a recap, what we are up to, we have a physical universe, we map to a theoretical universe or maths, and you can take a part or whole, and then you consider Hilbert space. And then this experimental thing or experimental apparatus, loosely speaking, corresponds to states. And what we can experiment, this abstract quantity, can be experimented, are observables, for instance, mass, charge of electron. And if we know at particular time, then we have a time evolution or dynamics of the theory that is given by the unitary evolution, which is called the time evolution operator. So that's a very big picture. Of course, all this requires even more discussion. So yeah, questions, comments? Okay, I do not see an immediate question. What is parameter define lower bound of the constant? Uh, it's not necessary there is a parameter that defines lower bound of Hamiltonian. It comes from that. So Hamiltonian is something which generalizes the notion of classical total energy of a system. Now, from classical mechanics, we have the experience that energy is always positive. Sorry, I have it called. Just a minute. Sorry. Uh, so if something has negative energy, that doesn't make any sense in classical mechanics. And that's how the postulate enters here. Although we will see that in quantum mechanics, negative energy can happen. Actually, in quantum field theory, uh, but that's not a part of this lecture course. So that's how the so if or you can put this way: if you do not have a lower bound of energy, the system can go lower and lower energy, and this will be an unstable system. So to make system stable, we need a bound, a lower bound for the Hamiltonian. Okay, does it answer your question? Yeah, you can consider zero. There is no problem. You can consider, yeah. Um, yeah, there is no problem. Yeah, of course. So zero is it's a natural thing. Yeah. Yeah. Any other questions? I mean, I wrote some constant instead of zero because that depends on your reference frame. So something is zero in one reference frame. This can be non-zero in other reference frame. But again, we just fix the reference frame and then you said, okay, zero in that because everything is frame dependent. Most of the things are frame dependent anyway. Okay, so I don't see any question right now, but yeah, again, if you have question, please have your in chat or unmute yourself and you can ask. So now I wrote just what is a state, and now I want to give a bit more we want to delve a bit deeper in the state because yeah, depending on situation, some of you have already told about entanglement entropy. So state can have different thing. So let's go to state business. So, okay. So this may or may not be familiar to all of you or some of you. So let me just recall anyway, so that we all are in the same setting. So if we have a vector space, Hilbert or not Hilbert, doesn't matter. So let's call V is a vector space. And we take an element of V and let's call it Vi. And we can consider its finite linear combination, by which we mean that you take some number or field Ci and element Vi. Okay, so that's the linear combination that you also know from linear algebra. But if these Ci's are from 0 to 1 and they sum up to 1, then this is called convex combination. Convex of Y is writing like this. Oh, sorry. Convex combination. Okay. Now you can also talk about convex subset. So you know what is a subset of a vector space. So let S is a subset of the vector space. And we will say this is a convex subset if it satisfies convexity condition, which means you take two elements from S. So V U V element of S, then Cu plus 1 minus Cv will be in S for all C in 0, 1. Okay, then it is called a convex subset. Okay, so once you have a convex subset, there is a notion of extreme element. So if S is convex, yeah, I did V naught, which is a specific element of S, is called extreme if it cannot be written. Let me write this way. If V naught, so if it can be written, that's how we will write, right? Cu plus 1 minus Cv for some lambda 0 to 1 and xy. Okay. UVS, but not the extreme element. And it's extreme if this cannot be. Okay. All right. Now let me introduce a definition that you might have encountered already. This is called the notion of rays of a projective space. So again, V again is just a general vector space over complex or real, doesn't matter. And we consider the equivalence relation. Consider equivalence. So U equivalent to V when, if and only if this is a scalar multiple of other for some C in K except of course 0. Yeah. And now what you do, you take the quotient space. So quotient space, you divide out by equivalence relation, and that is called projective space. Over V. So projective spaces are, you can scale, okay? You can amplify. And the elements of a projective space are called rays. So arrays are elements of this projective space. Okay. Now let me introduce some more definition that is, I think, more what is traditionally found in physics quantum mechanics textbook. So now we are in a Hilbert space setting because we are in a quantum mechanical situation. And our first definition is that pure states. So we have already defined what are the states. And now we want to define what is pure state. So pure states are extreme elements of the state space. What is this? Okay. And yeah, we denote it by, okay, if we did, yes, I will just write pure. Okay, and now you can say, okay, what about non-extreme states? Yeah, so we should also give a name, and this is called mixed state. Mixed state. These are not extreme states. Okay. Now, suppose C is given by a finite or countable, finite or countable combination of Ci, Phi, I. So if it is finite, then finite. If it is non-finite but countable, then we have to talk about convergence. And so it is such that the series converges. Okay. And what is this Phi's? Of course, they are element of Hilbert space. And they are not zero. So then this state, psi, so you take this state, and then if you put another element of Hilbert space, that will be a number, but we are not putting a number element. So this is not yet a number, rather than this is still an operator, right? You have to pick it something there. And then you put psi. So now, so this was an operator acting on this, and you normalized. So divided by I square. Okay. This is called coherent superposition of the state phis. So I dot I divided by. So some of you have read superposition. So that's how this, I mean, we are going towards there. Okay. Another terminology. So this is a state. if this satisfies rho equals to finite linear combination of some pi and rho I, where rho I are also element of state space and pi are something from 0 to 1, which sum up to 1. Then, okay, maybe I should write if. So if a state satisfy this combination, linear combination, then this state rho is called different than previous incoherent. Superposition of rho i's. Okay. One more. So you take an element of Hilbert space and take another element of Hilbert space, then this is a number, right? In fact, this is a complex number. And this is called transition amplitude. It's also called probability amplitude. So I write both probability amplitude of, so we have to take amplitude of what, right? Of this state. Amplitude of C on this state. Let me just call it C. Okay, so these are some terminology that we will use and you will see usually in physics textbooks. So any questions? Okay, I do not see any immediate questions. So bit again about terminologies. So the pure states, what does coherent and incoherent superposition principally mean? Okay, so coherent superposition means that you are superposing like this of states which are of similar type. So you are superposing objects which are similar type. I mean, how to say, like, okay, you are superimposing with apples, okay, or pears with pears. So similar object. So that's how. So they structurally they are similar, but incoherent is not. So this is row I and row J may be very different because they are just some state. Okay, so you are then super positioning apples with oranges, okay, to different object. Yeah, thanks for your question.
I just wanted to confirm this thing because in physics we use this thing as, for example, if I have a state psi and I can write it in basis like alpha time 0 or beta time 1. And while taking the expectation value or like the probability, I can make a density matrix, and the diagonal element of the density matrix would be alpha square and beta square, while the off diagonal elements were the alpha beta star and beta alpha star. So if we take these similar positions like alpha square and beta square, um, they are coherent superposition. And if we take the off diagonal elements, which is alpha beta star or beta alpha star, are they correspond to incoherent superposition? Is that what you mean?
Yes, but what you told is a special case of that in the following way. So what you wrote,
Mhm.
like, yeah, a density matrix can be written in that way. So if it is a pure state, I mean, I haven't mentioned it because that will be one of your homework. So pure state will
Mhm.
have some extra constraint on density matrix. Okay, it's basically
Okay.
rho square equals to rho. And
Okay.
if rho square equals to rho, then you will get that expression that you were talking. And then you get,
Okay.
and incoherent means that this can be a mixed state, right? So rho
Yes.
I square might be rho I, but rho j square might not be rho j. So you have mixing even in the state level. Or you can say, given a mixed state, you can decompose in terms of pure states and non-pure states. So this decomposition is in terms of pure states, and this decomposition has pure and non-pure both. Or even more physics language, pure states that I was going to write. Let me write it and then I come back to you. So pure state are state on Hilbert space, and these are element. I mean, you can write as element of Hilbert space, and then in physics literature, this is called wave function. Maybe I write this way. Wave function. Okay. And what you wrote, yes. What you said, yes. And this will be one of your homework, like how the usual expression you know from physics literature can be derived from this expression. So you can ask, because this might look a priori bit more complicated and less physically motivating, like why we are considering this. The reason is that if you go from this basis picture, then you have to treat pure and mixed state separately. In other words, for wave function, you can write one way, but when we do not have wave function, rather you have a mixed state, like thermal state, then you have to write something a bit a different way. But I try to do everything from the unified way so that pure and mixed, everything is inside. And that's why it looks a bit maybe cumbersome, but everything is there. Okay, and now some of you have already told. Usually, this mixed state, sorry, what is called state is called density matrix, and this is also called sometimes statistical operator. Okay, maybe I add it. Okay, let me add it here anyway. So this is also called density matrix or statistical operator. So this is some notion that actually introduced by John von Neumann. Okay, and now back to your question. Yeah, I'm not going to show, but maybe I put it. So maybe I write it. Okay, I don't have a space, but let's write it here. Yeah, it's not really definition, rather like a slow. Okay, it's not. It's like a wording. Okay, I write a diamond. So superposition. Superposition principle. So in quantum mechanics, especially in physics book, you will see the word a lot. So what does it mean in this language? Or what does it really means? It means that you have a pure state which can be written as a non-trivial combination, because of course you can write 0, 0, 0 plus 1. I mean, that's not interesting. Non-trivial combination, which means it will be some convex combination where at least 2 will be non-zero. Yeah, otherwise it's trivial combination. Combination of pure states. So it means that you have one pure state and you have another pure state. You take a non-trivial combination, like you are telling alpha, beta. So alpha time your pure state, something like I write your language, alpha pure, funny, it's pure 1, and beta pure 2, and this is another pure. Okay, something like that. And that's called superposition or quantum superposition, because you superpose. And I hope now it's clear why this is already included in this relation. Yeah. Okay, we talked about transition and probability. So I just add one word. So this is a complex number. If you take its modulus and then its square, this will be a real number. And this is called probability. So I write in blue. That a state at t given by the state vector c I write here following a measurement. Of course, at time t. Okay, so it's like that. Okay, you have, say, this is state, and you do a measurement at a particular, so you have this state at time t, and you do a measurement, and you do the measure. So measurement has also a state. So this is a measurement state, and this is like you have your initial state, and then you take their scalar product, you take their modulus and square. That is called the probability, and that's why it's called probability amplitude. Sometimes people do not distinguish between probability amplitude and probability just it is, yeah, because it's just a square. So yeah, for the first time, I think it's good to clarify what is what, but then there is no issue that if you are a bit pedantic. Okay, now I want to comment collapse. Yes. So now you see, if we take pure state, then it's called wave function, and that's the famous wave function collapse. So quantum mechanics officially, or at least structurally, so Heisenberg, first paper, 1924. So it's 102 years. And still, we do not have a complete understanding of wave function collapse. And this is, in some sense, contradictory with other postulates of quantum mechanics. Why? Because this is the dynamics, right? So given a state at time t, you have a evolution, and it's a unitary evolution. Very important, it's a unitary evolution. So given at t, you know what is happening after some other time, and you can put minus t, so before past doesn't matter. So then if you do an experiment after t plus tau, this is what you should get. But this is what you get. So you can physically think this way. You do an experiment, you get some results, good, and then you wait a while. Okay? And now your friend, he tells, I know how with time a state evolve. That's the unitary evolution. Okay, very good. And then he computes. Okay, and now you know what is going to happen after time t plus tau. You do the experiment and you will get this. You will get that from all the possibilities, only some particular possibility has been chosen by experiment. Some people will say, oh no, there is a more fundamental theory. Okay, let's come it later. So that means that you have a collection of possibilities. Among those, only one possibility comes out the experiment. And if it is a pure state, then it's called, so all other states collapse. So that's why it's called wave function collapse. And so historically, people, of course, do for pure state. So that's why it's called wave function collapse. But you can just do it for mixed state as well. And as you see, so there is a kind of inconsistency between these two postulates. And this is one of the reasons why some of the physicists think that quantum mechanics is an incomplete theory. Okay, because there are inconsistency, logical inconsistency between quantum postulates. There are several attempts to solve it, and still people are trying to solve it. So people who work in quantum foundation, they usually are concerned about these issues. And there are several theories about it. Decoherence, many world interpretation, Bohemian mechanics, okay? And none of this could really solve the thing. And this is also close to related to this so-called measurement problem. Okay, so far we do not have a solution of measurement problem. Maybe some of you will offer it. But yeah, that's one of the foundational issues. So quantum mechanics is an amazingly successful theory. In fact, it's generalization quantum field theory, but the foundation is not yet clear. So I don't know how you feel about it, but I found it very perplexing because practically it gives super result, but when you look at its foundation, the foundation is not very firm. I mean, some part is very firm, but there are issues in the foundation which is not clear. And some people also has this impression or idea that quantum mechanics or quantum theory is not actually the final theory of nature. The final theory of the nature will be something more fundamental than quantum theory, and this is one of the reasons, because this fundamental things has to be solved if nature is logical. So yeah, and that's the whole discussion. I mean, there are books about only about these issues, and people do PhD, they do research, and yeah, we are not going in that direction, but that's really fascinating thing. Okay, so now we have some idea about states, especially what is a wave function that usually, so usual physics books start with the notion of wave function. As I told, I like the other way around, because then everything from the beginning, everything is there, and you just say, okay, this is wave function, this is mixed. You could do the usual way also, and then you have to do it again for mixed state and some changes. But if you, yeah, maybe not very intuitively, but if you do this way, then everything is there. All right. So before I go to the next topic, are there any questions about the very basics of quantum postulates? Or comments, your thoughts? Not in the current situation, because the string theory suffer from all the, this problem also. So this problem is also, so string theory haven't managed to solve this wave function collapse problem. In fact, string theory hasn't solved any of the quantum foundation problem. So it may, I mean, there is no proof that string theory cannot, but so far string theory hasn't solved any quantum foundation problem. So that's why, based on current scenario, I mean, I would say I'm not optimistic that is going to be the fundamental theory, because I think, as I told, I think nature should be mathematically and logically and physically consistent. And if some theory hasn't able to solve this thing, then this cannot be a fundamental theory. And string theory has the same problem. I mean, the state wave function collapse problem also, because it is going from here. And string theory is based on this principle also. And I am not a string theorist, so I am not competent to really give you scientific criticism, but some of the things that is established, for instance, we are living in a four-dimensional world with no supersymmetry. Now, without supersymmetry, string theory doesn't work, and string theory requires higher dimension. So from physics perspective, this is not yet the fundamental theory. It may be in future. Yeah, maybe people manage to solve this issue, but right now it's not the case. Also, we know that universe is accelerating, and as far as I know, again, I'm not an expert, you cannot describe accelerating universe from string theory yet. So if you look at your observation, and if you ask your string theorist friend, I observed this, can you explain? Answer is no. Can you explain something that we observe? Maybe there are, I mean, I do not know, but at least there are something that string theory cannot explain, which we observe. It's an empirical fact. Another fundamental, I mean, equally important issue is the standard model of particle physics. So given string theory, can you derive a standard model of particle physics? The answer is not yet, maybe in future. So these are some of the limitations, and I think because standard model of particle physics is an experimentally proven fact. Okay, Higgs is a standard proven fact. So if a theory cannot explain this, this cannot be a fundamental theory. However, I must also tell that string theory has produced amazing, beautiful mathematics in arithmetic geometry, for instance, and it has beautiful dualities. So it has some very beautiful geometry, especially arithmetic geometry. So that also gives us some motivation, I mean, depending on how you see it, that since it has this rich mathematical structure in some of the mathematical structure, not everything, because quantum theory also gives very rich mathematical structure. So I say it has, I mean, I definitely say that, as I told, I am a skeptic, and which means that it may or may be. But since I haven't studied it, I cannot tell you very scientific criticism about pros and cons, any of things. Okay, but why it is even a problem? Why? Because measurement is not unitary. Yes, because you evolve. So you do an experiment at time t. You have this state, and then you wait tau, and you have this state. So you do experiment. You are supposed to get this result, but you get not the whole. You get only one of these results, and that is this one. So I give you maybe more pragmatic view. So say you have a electron system. Electron has this okay, I mean, if you take massive, so it has spin, the so-called up spin and down spin. And you do an experiment by, say, spin selector. So you take one of this spin. Okay, so after experiment, you have only one spin. Good. Now you wait, maybe say 5 minutes. And you do the experiment again. What do you expect? So if you start with up spin, after 5 minutes, the answer is this. But when you do experiment, you will see again it has up and down spin. So it's not only the unitarity. Of course, unitarity is the issue. But overall, so we cannot predict the experimental outcome from quantum mechanics. That's the incompleteness. So there are more postulates. So you take all the postulates of quantum mechanics, okay? And you prepare a state, okay? And there is something called uncertainty principle or theorem. We will prove it maybe next week. And okay, then you know what is allowed and what is not. Good. And then to be a theory, you should be able to predict what is an experimental outcome. And we have we know also how things evolve with time. So this is a unitary evolution, and this is a perfectly deterministic evolution. So that's actually, I mean, depending on your view, is a funny. So quantum evolution is a deterministic thing. It's even unitary, right? But problem is the quantum state, this we do not know with arbitrary precision because of something uncertainty principle, as I told, I will discuss later. And then you evolve it. So you know evolution perfectly. It's a perfect unitary evolution, deterministic evolution. Okay, very good. Now you do experiment after tau, you should get this. No, even if you take, so again, it depends on what you are experimenting. Okay, so you take a big ensemble. Okay, so no matter how big your ensemble, if you are taking electron, it will be either positive or negative. Yeah, so number of, if you add more electrons, it will not change in this context. Okay, and then you do an experiment, and you do the experiment maybe 5 times, and you say, I take the average. Yes, you can do that, but each time you do the experiment, we cannot predict the experimental outcome from our theory. Otherwise, we don't need to put this. So in a way, this is, I mean, okay, every postulate is by hand, but problem is, knowing a state or given a state, we cannot predict its experimental outcome yet. And no theory can do, no quantum theory, because this is, every quantum theory is using this thing. So we just do not know how to do it. However, if we, yeah, sorry.
I have heard it somewhere that, for example, if a doctor have 50% of, or let's say 60% of doing an operation and being successful, if it have the 60% probability, and if he tries to do the experiment and he failed, and then because every time the probability is 50-50 to be successful or fail, but if you take a big ensemble, if he tries to do the operation more, he will ultimately reach the success ratio, the success probability, which is 60%. So if he failed in first, let's say, first 30 operation, there's more probability of being successful in the next few, because the overall probability of being successful is around 60%.
Yeah, but your comment already contains this issue. So you call that is 60%. So by theory, you know there is 60% chance of observing something. However, now look at this equation. What does this equation tells? If you know this guy, you know 100% what is this guy. Because this is a deterministic evolution. So you see the problem? And also, even if you take arbitrary high number, I mean, of course, we cannot go to infinity for practical reason, but take arbitrary high number, still there will be some probability. You can say, okay, this is 10%, 5%, but it's still 5% probability. You do not know what is that. So it's like I have 5% probability of doing that, but still there is 95% chance, or so say we have 95% chance of being success, but still we have 5%. And it's only the experiment that tells you what is going to happen. So forget about this axiom or any. Let's try to build all possible axiom. Okay, forget even axiomatic. We want to predict something, right? That's theoretical physics. We want to predict. We want to predict our experimental result. So what we can do? And apparently so far, and we know actually how time evolves and everything, and still we cannot do it in perfect precision. So for instance, if you take pure state, then this is the Schrodinger evolution, or given by Schrodinger equation. That's actually our initial motivation. And if you look at Schrodinger equation, if you remember, it's basically the Laplacian and then probably some potential. Let's take you are considering free theory. So potential is 0. So you have a Laplacian. You know how to solve Laplacian. We have discussed it. You have some homeworks also. You know perfectly these things. Put boundary condition, whatever you want to that. You have very nice theory. And you then take this operator. Now you also know how to construct this operator. So what will be this operator? This will be a matrix of eigenvalues of H, right? Okay. And now comes this question. You do the experiment, you will not get all the eigenvalues of H. You will get some specific eigenvalues of H. And we do not know how to get that from theory. So if I write this way, what is this? This is loosely speaking. So E is the function. Then eigenvalues, or maybe energy, more traditional. Right? That's spectral theory tells. Okay. And now you say, okay, E1 has 95% possibility. Maybe you want, as you told, we do 30 times, 40 times, large times, this and this possibility. But still we cannot say whether this experiment give you E1, E2, E3. We have to do an experiment, and this tells us what we will get. But this tells that this is a unitary, it's a deterministic evolution. On the other hand, once you do the experiment, so it's like, okay, you have an evolution. You do experiment, then it instantly collapses one of the eigenvalues. Okay, so this instant collapse of eigenvalues, if I write this way, let's say, let's put E naught. Okay, so this process, so you have this, you do an experiment, you take some time, and after some time you get this. This you cannot derive from there. In fact, there, I mean, I do not know any quantum equation theory which you say you come from there to there. You have to go your experimentalist friend, you will do experiment, and then you see. So is it clear, this measurement wave function collapse issue? This is really a fundamental and conceptual issue. So yes, feel free to unmute yourself if you have comments, questions. Okay, so let's see who are still with us. So who is lost? If you are on screen, please respond so that we can discuss. Okay, probably not all of us are on screen. So thank you all who, for your answer. So I can see some of us was not able to follow. So those, could you please write me in chat, maybe in personal chat, if you do not, if you are not comfortable to share with others, so then we can discuss what the issue. Or if you like, definitely just unmute yourself and ask what's your questions, comments. Or if you can just tell. Okay, so there is a question. Is there any experiment about postulate 5, which is the time evolution? Yes. So for instance, if you take pure state, then this is given by so-called Schrödinger flow or Schrödinger equation. And I cannot give you a precise reference right now, but in atomic physics, there are numerous experiments where Schrödinger equation turns out true. One of the historical one is the hydrogen spectrum. Okay, so if you look at the spectrum of hydrogen atom, and you want to say, okay, how I get this spectrum, and then you use Schrödinger equation. In fact, Schrödinger was the first who did it, and he got perfect matching with hydrogen spectrum, and that's how people understood, aha, Schrödinger equation is the right equation. So yeah, leisure is also an example that come much later. So this is an also an example. So there is a interesting story also about Schrödinger equation. So Schrödinger first discovered what is right now called Klein-Gordon equation or relativistic wave equation. Okay, but that doesn't give right experimental result. So Schrödinger had to change his equation, and he changed it and finally got what is now called Schrödinger equation. And as I told, it matches with hydrogen atom and many more things. Okay, so fantastic. But after 2 decades, people realized if you add special relativity with quantum mechanics and something more that we sketched yesterday, you get quantum field theory. And the simplest type of quantum field theory, I mean, is from a real perspective, is the so-called scalar quantum field theory. And there, the equation is precisely given by the Klein-Gordon equation. So Schrödinger actually discovered the equation much before Klein and Gordon. In other words, Schrödinger was far ahead of time. He got one of the fundamental equation of quantum field theory. But since he didn't have any experimental result back then, only the results was non-relativistic, he changed his equation so that this effect is not important, and then he managed. So in a way, Schrödinger discovered two fundamental equations. And now we know from Klein-Gordon this route, but Schrödinger actually did it. Yeah, so there was someone else who were also not feeling comfortable. Could you please write your question? You can directly write to me if you do not want to share with others, and then we can address it. So do you want 10 minutes break as we talked yesterday? There will be additional 50 minutes lecture today to compensate Friday's lecture. Okay, thanks for your question. This Heisenberg equation of motion. Yes, this is related to this. Yeah, I forgot to write it where it is. Yes. So this is called Schrödinger picture. And take an observable A at time t tau. This is given by similar equation, just the other way around. So this is called Heisenberg equation. Yeah, thanks. So what's the difference? Difference is that Heisenberg equation of motion gives you evolution of observables, and this gives you evolution of states. So evolution of states, and this is evolution of observable. Okay, and that's actually a good question. I mean, every question is good. So historically, these two guys, of course, the founding father of quantum mechanics. So Heisenberg was doing. By the way, one remark. So always called Heisenberg equation of motion, but it was not derived by Heisenberg. Rather, it was derived by Dirac. So Dirac was too modest, so he didn't put his name, but it was derived by Dirac. Anyway, so Heisenberg formulated quantum mechanics in terms of matrices and in terms of observables. So, and Schrödinger, on the other hand, he was doing in terms of states. Okay, so when one needs to consider how a quantum system changes, for Schrödinger, it means that how a state change. So that's why in the state level, in the state level, this is the Schrödinger equation of motion. And so there was a time when it was not clear whether Schrödinger and Heisenberg was doing same thing. As I told yesterday, I think after 1 or 2 years, Schrödinger wrote a paper, and he showed that Heisenberg formulation and Schrödinger formulation is equivalent. Okay. However, there was not an equation of motion in the level of observables, and Dirac derived it. But as I told, being a super modest person, Dirac didn't put his name, rather he called it Heisenberg equation of motion, because Heisenberg formalism was in the level of observables, and that's why he called it Heisenberg's equation of motion. Yeah, more questions? You're welcome. So I asked this question, maybe I ask again. Is there any topic that you want to get reviewed or some basic material? Then I can ask to review that material on 21st of June, this tutorial. Relevant problems. Okay, I shall give a homework problem tomorrow, and then definitely they will be discussed. So another thing I want to ask, so next week there is 2 tutorial on 19 and 21st, and there is nothing after that week. So 27 and 28, and then 3 lectures week after that. So I was wondering, instead of 3rd of July, is it okay if I shift this lecture from 3rd of July to 27th of June? Maybe I put in poll. It's Saturday, our usual day. Okay, two. What about others? Three. Thank you. What about others? Because the reason is I might go to a conference. I mean, depending on visa, I do not know yet. So, and yeah, I didn't know the time at before when we were planning for this. So, this was unforeseeable. Okay, so thanks for of you who have responded. Uh, Others were not probably on screen. All right. So, do you want to take a 10 minutes break or should I keep going? Okay, yeah, I think it's good to have a break. So, we then start at half after 15 minutes. Yeah. All right. So, then after 15, we start after 15 minutes. Welcome back, everyone. Can you hear me? All right. So, the topic now we are going to discuss is about this time evolution. I think it's fairly evident why this operator is ours of importance, because that gives you our evolution. And of course, if we have a self-adjoint operator, we know how to define bounded functions. But in this case, we have actually more, say, direct way. In fact, so the way this is defined, given age, we have this operator, but this is actually both way. Given this operator, there exists as h, so you can also reformulate this axiom in entirely in terms of ut, and then you derive h. That is also possible, or the way it has been done, that is also possible. So let me show you this link, and that's very useful in usual quantum mechanics. So the topic is our strongly continuous one parameter unitary groups. Sometimes we just use the word flow, especially if there is someone from differential geometry or PDE, then flow will probably more familiar word to you, the same thing. Okay, to begin with, what is this word strongly continuous? So when we define operators on Hilbert space, we haven't talked about their topology or convergence. And so let me introduce now two of those. So we have the operator on Hilbert space, or even a norm space, okay, because we need norm. So we say T is our operator, and it's sequence of operator Tn. This converges to T strongly. By strongly, as written here, means that in strong operator sense, but in a strong operator topology. Okay, what is it? If for all u in the vector space or normed vector space, limit, so you act in u, and this will converge to tu. So it's a number, so you take norm, and this n tends to infinity. Okay, so a strong sense means you act on a vector, and then it converges. Sorry. And there is another related, so it's strong, maybe we call the other this weak one. So weak one is in the sense of dual. So we have already introduced the notion of dual. So, oh, sorry. Tn converges to T, sorry, in the weak operator sense. or it's also called weakly, if for all u in the vector space and f is in the, oh no, why? Dual, so we put dash for dual. That's really annoying. I don't understand what's happening. Ah, okay. I think I understood it now. Mhm. Okay. Limit n tends to infinity as before, but now weak, so in the sense of dual. So how you put dual? So Tn as before. This is an element of the vector space. And then you take the dual. So f, this is a number. This is equals to this number. Okay, so that's a weak sense. Okay, now let's get back what we are up to. So definition. So as before, H is a Hilbert space. And we consider a collection of bounded operators, ut, t belongs to R, on the Hilbert space. And this is called one parameter group of operators, called one parameter group of operators if basically the group property. Yes, recording is ongoing. Yeah, I should have paused, but okay, thanks. So this equals to identity. And now the group property. So ut for all ts in R ut. It's a composition, okay? I'm not writing composition. U t plus s. Okay, so now we know what is one parameter group. And now what about strongly or something? So now we put a bit sub. So again, this is called one parameter unitary group. I think it's fairly understandable. If ut is unitary, all t. Okay. So this is called weakly continuous. So whenever we say continuous, we have to say continuous where? So continuous at t naught. Okay. Okay, I want to make life a bit easier. Let's write both respectively strongly. Continuous. If the mapping T maps to UT is continuous at T naught in the weak respectively strong sense. Okay, that's why we introduced it before. And as you know from reanalysis, if it is strongly continuous for all T at R, then we just say this is weakly continuous. Okay. Now, perhaps the most fundamental theorem in this business. This Stone's theorem. It's also called von Neumann-Stone's theorem because both obtained it. So von Neumann has actually slightly different thing, but okay, let's put anyway. Stone was a famous American mathematician who contributed a lot in operator theory. Okay. So as before, H is a complex Hilbert space. And UT is in R, which is bounded operator on H. So it's a family of operator, yeah, satisfying the following two conditions. One, so by this S limit, I mean limit in the sense of a strong operator topology. Okay. T tends to T naught. UT equals to UT naught For any T0 in R. And number 2, there exists some positive constant such that the norm or operator norm of this operator is bounded by this. Right here. Such that for all t, this is bounded by this. Okay, so these two conditions. Then Mr. Stone tells us that for any integrable function f on Rd, there is a unique operator there is a unique operator integration over R f of t ut dt which is a bounded operator. So I hope now you know what this means, because we discuss operator valued integration, right? Oh no, sorry, this is not operator valued integration in the sense of measure. I will define it. What does it mean? Sorry. Okay, we haven't defined it such that, let's define it. So this is function, there is no problem. And then we have this operator dt integration. Okay, that's the operator. Now we act on an element of a vector and take scalar product with any other element. This is actually defined by this equation, and the definition is, so you take f. So how operator acts? It acts on function. So you basically define it so that this operator acts on function and then integration over f. So phi psi ut. Okay, now this is an operator of t, and now you integrate dt. So this is of course in h. Sorry, this, and it satisfies. So this operator several properties. So maybe I use AB for all C in H. So we have this operator ut dt psi. Oh no, sorry. And yeah, this integration, and now norm of this I'm really surprised why it's happening now. Less than equals to, this is bounded by integration over r f of t absolute value, and then the operator ut psi. This is the norm in the Hilbert space dt. B, if A is another bounded operator on H, then A integration ft ut dt, this equals to, so you can take A inside. It's like the usual calculus rule, but in the level of operator. Ut dt and integration of ut, sorry, ft ut dt. A, if you take the other, I mean, from the left, then the same, but from the left. ft ut a dt. Okay. See. Sorry. I make a typo. Sorry. This is, let me put n, rn. So rn okay, since we put n, let's also put n here. N n n n n. Good, I didn't wrote. And okay, and now comes n equals to 1 case. So if n equals to 1, then from t to s, f of tau u tau d tau, this is then defined as integration over r g tau f of tau u tau d tau, where g is the characteristic function from or on, of t to from interval t to f if s is greater than or equals to t, and g equals to minus of s to t if the other way around. Okay. In this case, we have two further properties, that the map from R2 element of S and T, that maps to the integration we wrote earlier from S to T, f of tau u tau d tau. So this map is continuous in the uniform topology, I will come. What is uniform topology? Just let me finish it. And if continuous implies in the strong sense, so it's not minus, okay? S, maybe I put color again. S dt from S to T, so U tau d tau equals to f of t ut. I need a space, so for all S T in R. So again, fundamental theorem of calculus, but in the level of algebra operators. Okay. So that's yeah, okay. There is an issue. I wanted to introduce it, but this is not really strong. So this is just one theorem that we need for later. Yeah, strong theorem we are coming. Okay, so what the theorem tells that you can actually consider this integration, or integration of an operator. Yeah, so we haven't introduced. Okay, I just come back to this thing. So what is written here is basically very simple. So what we know for usual integration. So what we know for usual integration is that we can integrate a function, and we also learn how to integrate with respect to an operator valued measure. What we haven't learned, how to integrate a operator. So you see it's integration of a function and with an operator. So that's the whole point of this theorem. So thanks for your comment. What we are up to. So first, what is this definition? So definition is that how you define this integration, you just act this function with any two vector and then scalar product. Now it's a function, and then you can integrate. That's all. Okay. So that's the main thing we want to say. And once we have a defined integration of a function, then it's natural to ask whether the other rule of fundamental theorem of calculus and this thing's true. The answer is true. Okay, I understand it's a very long thing. So maybe I do not go. Okay, so that's all. That there is nothing more. Okay, then can I just take 5 minutes more? Yeah, so I want to finish this. Yeah, thanks a lot. So now we come to Stone's theorem, and that's why I wanted to introduce this notion, theorem Stone. And I believe all of you will enjoy this. Okay, so as before, Hilbert space and H. This is not Hamiltonian, okay? Just an operator from domain of H to H. Okay, lots of H. And this is self-adjoint. As usual, we denote pH by its spectral measure. By now, you all know what is this guy. Okay, now the operator you have seen before, ut e to the power I t h And how, I mean, I think you know it, but just in a formal way, you define it using this spectrum of H, and then you know function of operator means function of eigenvalues. So function of I lambda t, and then remember, we know how to integrate with respect to operator valued measure. So this is functional measure H lambda. Okay, that's, I think, more or less you expected. So the catch is that this is what you get from functional calculus, but this is strongly continuous. Okay, first. And now we want to differentiate an operator. Before we integrate, we want to differentiate. What does it mean? Again, same sheet. So you take, not sheet, S for strong. So you differentiate an operator. What does it mean? Similar. You act on a vector, and then differentiating means you take the limit, right? Because, I mean, it doesn't make sense to differentiate an operator. So you said you just act on a vector, and then you do the usual thing. So that's what means differentiation of an operator. So this limit exists. So you should know a function is differentiable if this limit exists. So this limit exists in H when, if and only if psi is in domain of H. So today you see again why we are so much into domain. And what you get by differentiation? You get du by dt at t equals to 0 psi, like the usual functional differentiation, I t psi. Okay, and now the final thing. So if ut is a strongly continuous one parameter, strongly continuous one parameter group of unitary blah blah blah, then there exists a self-adjoint operator H, by which of course we mean from domain of H to H, such that okay, e to the power I th for all t in R, ut equals to e to the power I h. So thank you all for your super kind patience that you allowed me extra 1 hour today. And the message of this theorem is that if you forget all the technicalities, you learn how to integrate an operator, how to differentiate an operator. And if you have just a strongly continuous unitary operator, then the existence of this operator H is automatic. And you also see the other way around. If this is given, that's probably more or less expected from a spectral theory. And that's, so Strong says that the other way is true. In physics literature, this operator usually turns out to be Hamiltonian. So if you assume that your flow is strongly continuous, then the existence of Hamiltonian is automatic by the Stone's theorem. And if you assume you have a Hamiltonian, then of course you have a strongly continuous flow. So if you remember the axiom 5, we can now restate axiom 5 in terms of the time evolution is given by strongly continuous operator, which tells that there exists a Hamiltonian. Or if we assume there exists a Hamiltonian with these properties, then of course. And Strom theorems just you can come back and forth. So you can reformulate or re-express axiom 5 the way around. And that's the main point of the Strom theorems. So thank you super much for your super kind consideration. Yeah, I do understand you all are super tired after this long lecture. So I can only thank you. And yeah, if you have question, I am here for 5 minutes or more if you need. Otherwise, thank you all.